then if you can. Could you hand them this homework to him? You know him? He's in 307. Well, leave it here because people will keep him. Oh, you're going to leave in the lesson? Where you going to leave in the
No.
Okay, thanks. Okay. Okay, yeah. All right, I won't do this all the time, but just to get to know your names, I'm going to hand in the homework just real quickly. For the people who sit in the back, I'll hand it in and let it go in the back. Pavel Mount, Omar Bach, Ann Newell, here, Carson Wong, not here, Fartian Creek, Joyce Ling, Head Lee, Uday Reddy, Johnson Lam, Ming Shan Sun, Rangit Siakun, Nicole, Aaron Floyd, Jacoby Hickinson, Hanyi Wang, Tina Shen, Jingo Wong, Andrew Chang, Ben Cook, Mitchell Cow, Alan Gu, Alan Gu, Keneet Gupta, Jonathan Sao, Young Van, Li Kang, Aaron Chow, Hussein Powell, Valerie Chang, Mariam Vora, Min Jong Kim, Sue Jun, Jorong Radford Ray, Portia Jones, Lee Yang, Xiaoling Zhang, Kevin Wang, okay. Peter Cam, Hai Nguyen, Nam Pham, Sridhar Mubarak, okay. Ruth Lang, Andrew Hatch, Sean Powell, Matthew Moon, Leon Tek Pang, Wonsup Sim, Peter Sang. You're my advisee, right? No. Oh, okay, yeah. Tiffany Crawford. Okay. Zakir. Okay. How do you pronounce your last name? Sun? Correct. Stephen. Lane. Stephen Lane. What is just your name? Sue Tong Ching and Amin Hajimura. Sandeepan Misra. Very good. Okay, so if you have questions on grading, then I think the best way to do this is to have him record the grade each time before he gives it to you, because when they have problems, they go to pen and all that. Okay, so questions on grading. Go to the grader, who is Tin Nguyen. Did I spell his name right? How do you spell Nguyen? N-Y-G-U.
N-G-U.
Y, yeah. Okay, you got it. And his email is... Okay? So,
Actually, I have 3 more. So I have 3 more homeworks from people who I don't have listed as officially enrolled. So if you're one of these 3 people, just make sure that you somehow get officially enrolled. There should be space. So it's going to be Bharat Sinha.
okay. So you should see Jennifer Hall, who is on the second, on the second floor of Corey. There's a room called Undergraduate Matters. If you go to her and say, Professor Zakir said I should get in, then she'll let you in. There's some issue which recitation you get in or something, but don't worry about that.
Jingyi Xiao. And Hui Wan.
Okay, let's find it here. Okay, so we had about 65 homework candidates. So that's roughly the size of the people in class. At the end, yeah, question. I was just going to make an announcement. I got an email on Wednesday right after I talked to you from Dave Kaspiak. Oh, he's in the room. There's some student who tells us that the Monday lecture, is still not online.
It's posted as a Wednesday lecture.
It was.
Or something like that. It's says makeup Wednesday, so it really should be Monday.
Oh.
Posted on the 17th.
Pardon me?
Posted on the 17th on the website.
Not the actual date, which was the 8th. Is that right, Dave?
Well, I don't know. I think they label it makeup lecture. I don't know what they...
Okay, but would all the lectures now are online?
They should be.
Okay, it's not that we made it up a different date, and therefore that date's lecture is not online.
Right. They should all be online.
Okay. So there was a bit of a miscommunication, but I sent an email to Dave. I called Dave on his cell phone, and he immediately, within like a couple of hours, he put it on the website on Wednesday afternoon. I'm sorry if the labeling was not correct. So just a quick show of hand. I mean, this was an issue. How many of you actually watched the missed lecture? How many of you watched the missing lecture online? Quite a large number. And of those, how many actually missed the Monday lecture as well? And that's why they watched it online. Okay, so some people just watch it because they want to watch the thing again. Okay. I want to do another real quick show of hand. How many hours took you to do this second homework? So how many people took less than 5? Between 5 and 10? Between 10 and 15? And larger than 15? All right, I think yours has to do with because you missed the lecture, and that was a big part of it. Did you also miss the lecture?
No.
Okay, you were at the lecture. Okay. All right, very good. So are there any questions or comments before I get going on today's lecture? Dan, do you have any announcements to make, or?
So we have graded solutions, or not graded. We have the solutions, and if there aren't enough, then we'll run some more copies for you. So. And also, if you want solutions for homework 1, go to see Rosita.
Right.
Rosita
Right. No, I deliberately do not do that. And for the following reason is because I don't want the electronic copy of the solution to be floating around Corey Hall. Because it's just better not to have the, if you want the solution, just go to Rosita and either pick it up at the end of the lecture. For example, today's solution is here. And then, for graded homework you don't pick up, you also go to Rosita. I just prefer not to have the solutions in electronic form. You can email it to the rest of the world, if you will. Very easy. Good ideas. Any other questions or comments? Okay. There is a slight possibility that I will not give Wednesday, September 24th lecture, in which case Vito Day might do that, one of my senior graduate students. But at this point, it's a little bit unclear. So I appreciate your patience. And then just one more thing is that there's a makeup lecture on, so let me write it. Makeup solutions plus graded homework from Rosita. Alvarez, 558 Corey. And then the other thing is makeup lecture. It's going to be September 29th. So even though I don't give the lecture on the 24th, there's no reason for a makeup because Vito will do that for me if I'm not here. But at this point, I'm not certain whether that's going to happen or not. Any other questions or issues? So we're just about done with chapter 4 of Oppenheimer and Schaefer. And we're going to move on now to some filter stuff, which is sort of some of the core material in this class. So what I'm going to talk about today is just a little overview of FIR and IIR filters, and then talk about difference equations and why and how a difference equation corresponds to an LTI system and whether it does and what conditions has to satisfy for a difference equation to correspond to an LTI system. So let me begin by having a sort of a generic discussion on filtering. on FIR and IIR filters. So to begin with, I'm going to start by posing a question to class. What is the predominant way of implementing LTI systems? I don't mean realizing it like in hardware, whether it's ASICs or microprocessors or general purpose DSP chips, and I don't mean that question, but what I'm trying to ask is, so here we are. Could you focus on the paper? Here we are. We have these LTI systems that we've been talking about for a long time, and what we've talked about, the beauty of LTI systems is that they have a thing called impulse response, and which we call H of n, and so what? Now I want to process a signal and get the process, and this is an LTI system, and X goes in and Y comes out, and I want to compute Y. How would I go ahead and do that? Convolution is the answer. X convolved with H is equal to Y, and we talked about this a little bit at the beginning. So what if I have an H of n that's like this, very, very long. Let's say H of n is a to the n u of n. Okay, it's dying exponential as a function of n. I would have a terribly hard time to convolve x, my input, with something that's of infinite duration. Okay? And so how would I go about doing that? Z transform, but like, can I program something called Z transform? That's the correct direction, but what do I do in the Z transform? What's the actual way I implement, let's say, a filter like that? Right, I already give you a lot of clues. You write it, you take the Z transform of this, and then from the Z transform you can write the difference equation, and difference equation is a way of implementing a filter like that. So broadly speaking, what I'm going to give my spiel again about filters. LTI systems or filters are categorized into two kinds of them. There is a finite impulse response, which we call FIR, and what that means is that their H of n has finitely many non-zero values. So it has H of n has finitely many non-zero values. And then there's IIR, which means infinite impulse response, which means that it has infinitely many non-zero values. So that means it has infinitely many non-zero values. Okay? And so this H of n that we had here, a to the n u of n, was an example of an IIR filter. Okay. Now, as I've discussed before, IIR itself can be categorized into two groups. Okay. IIR filters that have what's called rational transfer function, and IIR filters that do not have rational transfer function. And transfer function, I mean the Z transform of H of n. Okay, so here you got H of Z is equal, and what does a rational transfer function mean? Ratio of two polynomials. So rational means ratio of two polynomials. So then H of Z is P of Z over Q of Z, where each of these guys are polynomials in Z. And so polynomials are incredibly nice functions to be dealing with, and ratio of polynomials are also nice functions to be dealing with. Can anybody say why polynomials are good to deal with? From a mathematical point of view, what nice property do they have? Yeah, they're continuous and differentiable, infinitely many differentiable. You have a polynomial of order n, you can differentiate it many, many, many times, and you get the function itself is continuous, the derivatives are continuous, the derivatives all exist, nothing to worry about. And essentially there's a whole field in approximation theory, it's called rational approximation, if you will. And what it is if I have an arbitrary function, suppose you did a whole lot of experiments in the lab, And what you want to do, you want to fit a model through your data points. There's many ways of doing that. One way is to say, oh, I fit a polynomial model. Another way is I fit a ratio of polynomials. Another way is to say I want to fit, splines or whatever the thing is. But it turns out that rational approximation is one of the best ways of approximating arbitrary sets of data. How do you think that simple equations like F equals ma, how do you think those came about? I mean, obviously, I didn't have a personal discussion with Newton to find out how he did it, but you could, if you want the high school students to discover that, you could plot data and fit curves and stuff like that. So ideally, you want to fit the simplest curve that explains your data. But if that doesn't exist, then you might have to go into high-order polynomials or something fancy like ratio of polynomials, etc. But the real disaster happens if your IR filter doesn't have a rational transfer function. An example of that is the sinc function, okay, which corresponds to the box. So when you have a rational transfer function like this, okay, then let's say, for example, for this example that we had here, what's the transfer function of that? It's equal to 1 over 1 minus a z inverse with region of transform, with region of convergence larger than a. For example, if we're assuming that it's if it is causal, okay. So if that's indeed the case, then how can I? So if I'm dealing with FIR filters, it's pretty easy to compute the output. So y is a convolution of x with h. And so I can just write it down. Y of n summation over k, x of k, h of n minus k. And because there's finitely many non-zero values here, this summation is not terribly difficult to do. What do? Well, I have my x of n coming in. It's my speech signal or my voice or whatever sample. I got my h of n. And my h of n, let's say, looks like this, 5 points. Then how do I convolve? Would I flip this thing this way and then multiply these points and drag and add, all those things you've seen. So convolution, when you have fine FIR filter, convolution is easy, doable. Okay? You can easily see how you would do convolution. However, when you have an IIR filter, we won't even talk about implementing this, but we will talk about implementing this, and how would you go about implementing this guy. So for IIR filters with a rational transfer function, we use difference equations to implement them. I call it DE, stands for difference equation. So what do I mean by that? For example, suppose my h of n is a to the n u of n, and my h of z is 1 over my minus a z inverse. And x goes in, and this is h of z or h of n, and out comes y of n. Yeah, question? Should be what? Pounded? Bounded. No, hold on. If just because you have infinitely many samples in your h of n, it doesn't mean it's unstable. It doesn't mean h of n is not absolutely summable.
So I'm asking, why do we use z-transform? Does Fourier transform actually more powerful?
No, that's not true. Fourier transform is a special case of z-transform.
So you can define things like cosine Fourier transform if you can with z-transform.
Yeah, but you can also deal with filters like a to the n, z to the n that are unstable, that you couldn't deal with.
That's what I'm asking. If a filter is supposed to be stable,
Mm-hmm.
then why should we use z-transform? Because we know it's going to be stable.
Well, maybe not. Maybe there are many, because z-transform can be used for stable and unstable. So I mean, yeah, you could use Fourier transform, but z-transform, a special case of z-transform, when z-transform exists on the unit circle of the Fourier transform. So in my mind, it's a more general tool. So that'll be my answer, sort of, for using that. Because we're also going to be dealing, let's say, with anti-causal systems, or well, that doesn't deal with stability so much. But that doesn't deal with the Fourier transform issue. But you could just as easily do that. It's just that for steady state analysis, Fourier transform is good. However, when you have initial conditions, and it becomes clear when we deal with difference equations, when you have difference equation, when you have initial conditions, because you can deal with the one-sided Z transform, which I haven't talked about, it becomes a more powerful tool. Let this discussion go. If at the end of, let's say, today's lecture or Wednesday's lecture, you still have an issue, I'll come back to it. But you're right. You could use Fourier transform just as easily. Yeah.
Could it be that for certain systems you might want to have an unstable system, but one that would be stable for certain classes of inputs, and you know it's only going to see those inputs?
Right. Possibly.
And
But
why
in my mind, Z transform, is a much more general tool than Fourier is. There are many signals and many systems for which Fourier transform doesn't exist, and Z transform does. So that's sort of my primary reasons for sticking. And also, Fourier transform is generally used for steady state analysis. Z transform is better when you have initial conditions and things like that. Okay, so here's the here's our system, and so what we can do is just apply the convolution and say y of z is x of z times h of z, and in this case it's x of z times 1 over 1 minus a z inverse y of z. And so if I cross multiply these things, what do I get? I get y of z times 1 minus a z inverse, for example, is equal to x of z. And now if I take inverse z transform, what I get is, well, y of z minus a z inverse y of z is equal to x of z. And if I take the inverse z transform of both sides, I get y of n minus a. And what's the inverse z transform of this guy? Y of n minus 1 is equal to x of n. And so this is this is a difference equation, and I can easily implement that by having x of n coming in, y of n coming out, and we'll talk about flow graphs and things like that probably 2 or 3 lectures down the hall. But here comes y of n. You feed it into a delay unit, and delay is just a z inverse. And in practice, what's a delay unit? In electric, it's just a flip-flop. A flip-flop is something, for those of you who are mechanical engineers, something goes into it, and then the next clock cycle it comes out. So the next clock cycle is the same as a delay. And out comes, so this is y of n at this point, this is y of n minus 1 at this point, and I add these two things together. This is a summation node, and here I get x of n. Oh, and then I have to scale it also by a. Y of n minus 1 is scaled by a, so put a scaling factor a as well, and this is, at this point I get x of n plus a times y of n minus 1, and that equals y of n. So this difference equation with this flow graph is the IIR is the implementation of this infinite impulse response filter. All you have to have is delays, scale factors, and sums. Okay. And boom, you've implemented this thing. So what can we say about this difference equations, which is really the topic of our discussion today? What kind of a difference equation is that? First of all, it's what? Is it linear or nonlinear? And what do we mean? It's linear. And what do I mean by linear? It means that the terms x's and y's are involved in this equation in a linear fashion. That means there's no x squared of n, or x squared of n minus 1, or y of n squared, or x of n times y of n, or x of n times y of n squared. None of that. If it had those, it would have been nonlinear. So this thing, y of n comes in, its coefficient, y of n is coming in, y of n minus 1. There's no terms that are x squared or y squared or x times r. So it's linear. And what else can we say about this difference equation? What can we say about its coefficients? The coefficients are constant. And what do I mean by they're constant? That means they're not a function of time. So, okay, so coefficients are constant. What are they? For example, a. Okay, but if it would be non-constant coefficient, if I had like n times y of n minus a n squared times y of n minus 1 or something like that, because then the coefficient changes as a function of time. And that would make it a non-constant coefficient type of difference equation. So putting all of these things together, what can I say about this equation? What can I say about this guy? So I can say this is a linear constant coefficient difference equation. And it's very good, so I call it for short LCCDE. Okay, and it's very good for implementing IIR filters with rational transfer functions. So this is used for implementing IIR filters. Filter, I mean LTI systems. If I talk about IIR, it means it has infinite impulse response. As soon as the word impulse response comes in, it is LTI, right? It's good for implementing IIR filters with rational transfer functions. Okay? So, having said all of these things, now I want to flip the question on you and ask you the following, which is, under what if I now give you a LCCDE, a linear constant coefficient difference equations, under what condition does that correspond to an LTI system? You might say, oh, you're just taking us in a circle. You told us that you can use it to implement IIR filters. But there's a lot of nuances with regards to initial conditions and other things that you have to worry about. So, and it becomes clear as the lecture goes on. So the question I want to address today is, under what conditions does LCCDE correspond to an LTI system? Furthermore, under what condition does it correspond to a causal LTI system? Or, for example, causal LTI system. What has to hold true for this to happen? And I'm going to start by a very rudimentary example, okay, to illustrate all my points, okay? So suppose that I have a difference equation that goes like this. Y of n is equal to a times y of n minus 1 plus b times x of n. And my claim is that this thing doesn't even define a system, let alone an LTI system. Can anybody, do you think I'm right? Am I wrong? Can anybody say why this is not a system if I'm right? That's correct. So this is not really even a system because it doesn't have initial conditions. And I'll show you why. So I show you with a simple counter example. So does not correspond to a system even, just a plain system. Why? A system is something that a unique input goes in, a unique output comes out. That's what a system does. It's a transformation of a signal, okay? But in this case, I can show you that I come up with one solution, y of n, that satisfies this equation, and then I come up with another solution, y2 of n, that also satisfies this equation. And you can see that those two things can both be the solutions, and so therefore a unique input doesn't result in a unique output, and therefore it's not a system. So for something to be a system, you need to have unique input correspond to a unique output. Okay? So let me just give you an example. Suppose y1 of n is a solution to this difference equation. Then I'm going to show y2 of n, which is y1 of n, plus k times a to the n is also a solution. And showing that is incredibly easy. Why? Well, assume y1 is a solution, then what do we conclude? That means y1 satisfies this difference equation. That means y1 of n is equal to a times y1 of n minus 1 plus b times x of n. And we have the question, we ask the question, does y2 also satisfy the equation? Question mark. Well, let's plug it in and see if it satisfies this equation. Is it true that y2 of n, and I put question mark because we still don't know, is equal to a times y2 of n minus 1 plus b times x of n? Well, plug in the value of y2. On the left-hand side, it's y1 of n plus k times a to the n. And I still put question marks because we don't know. Is it true that it's equal to a times, what's y2 of n minus 1? Well, y2 of n is this. y2 of n minus 1 is just replace all the n's with n minus 1. So you get y1 of n minus 1 plus k times a to the n minus 1 plus b times x of n. So is this thing true? And after you do a bit of a manipulation, you realize it is true because this is true, right? If I plug in instead of y1 of n this expression here, because I'm assuming this is true, I plug into this here, I can quickly see that this thing is true. So the question marks are gone. So you see why? I plug in, this is y1 of n, I plug in this right-hand side. I assume y1 is a solution, and I ask would a y2 of this form, which depends on y1, will also be a solution? Will it also satisfy the difference equation? The answer is yes, it does. So here we go. We got two answers to the same difference equation. So that it's not even a system. Now, how do we fix this problem? Just like somebody said, we have to add initial conditions. Okay. So fix this by adding IC. IC doesn't stand for integrated circuit. It stands for initial condition. Okay. Then my claim is that then with IC you get a system. Okay. So let's write it down. So I say y of n is equal to a times y of n minus 1 plus x of n, and I let x of n to be some sort of an input like b times delta of n. And I impose the initial condition that y of minus 1 is y naught. Now can I come up with a unique, with this unique input, can I come up with a unique output? And the answer is certainly yes. What is the unique output? Well, we can do it one of several ways. One is we can do it by inspection and trial and error. The other way we can do it using using particular solutions and homogeneous equations and then applying the initial condition. But let me do it both ways so you can see an actual way of solving difference equations. So how do I solve this? Well, consider two cases, n larger than or equal to 0. Why? Because this delta of n is kicking it at 0, so I'm going to consider one n larger than 0 and one smaller than 0. So what I get is y of 0 is equal to a of y of minus 1 plus b times delta of 0, which is a times y of minus 1 is y naught plus just b. Then y of 1 is a times y of 0 plus b times delta of 1. Well, delta of 1 is 0. A times y of 0 is just a times a y naught plus b. So what you get here is a squared y naught plus ab. And you can just keep on doing that, and y of 2 the same way, etc. And what you find is that for n larger than or equal to 0, you can do the same thing. You get y of n is equal to a to the n times a y naught plus b. You can sort of do it by induction, if you will. And then repeat the same thing for case 2. Okay, so case 2 is for n smaller than or equal to minus 2. Why am I not considering minus 1? Because I already know my initial condition says that the answer is y naught for minus 1. So that I'm all set. So I'm going to go negative for minus 2. And what I get is y of n is equal to a times y of n minus 1 plus x of n, which is the same as, now I have to do a little bit of rearrangement. I can't compute y of n from y of n minus 1. Rather, I have to flip things over. I have to compute y of n minus 1 from y of n. So then a times y of n minus 1. What I mean is this. A times, I rearrange this thing, is equal to y of n minus b delta of n. And then y of n minus 1 is equal to 1 over a y of n minus b over a delta of n. So now what I do is I start plugging in. I let n equals minus 1. And if I do that here, I get y of minus 2 is equal to 1 over a y of minus 1 minus b over a delta of minus 1. And why do I do that? Because now I know y of minus 1, and I want to compute minus 2, minus 3, minus 4. That's why I rearrange this equation. This difference equation is just merely an equation. There's two different implementations. You can either compute y of n's from y of n minus 1s or the other way around. Now that we're going in the negative direction, we're computing the y of n minus 1 from y of n in this manner. Okay? So this difference equation, in a sense, has two implementations. It has a causal implementation, which was here. Here we computed y of n from y of n minus 1. And it has in this case, it has an anti-causal implementation where you're computing n minus 1 from y of n. I'll talk about this concept of a difference equation having multiple implementation, causal and anti-causal, in just a second. By the way, one thing that I found confuses people in the homework is anti-causal does not mean non-causal. Those are two different things. There's a thing called causal. We all know what that is. Anything that's not causal is non-causal. But anti-causal has a separate meaning. Anti-causal means impulse response is non-zero for negative values of n. So not everything that's non-causal is necessarily anti-causal. Okay? All right, so here's the answer, and I can compute. So what is this? It's 1 over a times y naught, and this is just 0. And then y of minus 3 is, I can repeat the same thing. It's 1 over a squared y naught. Da 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 da. And what I find is that for n smaller than minus 2, you can generally find a of n is a to the n plus 1 times y naught. Okay? And if I let n equals minus 1, I get y naught. I get minus 1 plus 1, 0, a to the 0, 1 times y naught. So even for n smaller than or equal to minus 1, I get y of n is equal to a n plus 1 y naught. Okay, so that's one set of answer I got, and that was another set of answer I got for n larger. This is for n larger than 0 and n smaller than 1. If I combine those two things together, you can easily see by inspection. So combine the two answers, and what you see is that y of n is just this thing times u of n. It's a to the n a y naught plus b times u of n plus a to the n plus 1 y naught u of minus n minus 1. So this is the negative going, this is the step function going backwards, and this is the step function going forwards. This is n larger than this and smaller than this. If you do a little bit of manipulation, what you find, adding everything up, is that y of n is at the end a to the n plus 1 y naught plus a n b u of n. So that's the final answer for everything, for all n. It turns out some of these things cancel out each other, and this cancels that, and we can combine them, and you see this thing plus this thing, the u of n and u of minus n minus 1 gives you this answer with no u's, and then this thing with u of n comes right out. How else could we have solved this problem? Well, we could have just done it through Z transforms and homogeneous equations and stuff like that. And again, for completeness, because this is not in Oppenheim and Schaefer, it's really just in Oppenheim and Wilsky, which is a textbook, unfortunately, none of the ECS undergraduates at Berkeley use. But for that reason, I want to go through this example very thoroughly. I know you haven't seen this piece that I'm talking right now, and it's not in the book either. So let's just come up with an aliter to solving this problem. So this is the thing you learn in like Math 1A, the first introductory math level at college. You have a difference equation or differential equations. How do you solve it? You first find what's called the homogeneous solution. I call it y sub h, and then you find a particular solution, and I'll explain what these are in case you forgot in just a second. And then you combine them. You write y of n is y sub h of n plus y sub p of n. And then you impose initial condition. So those are the 4 steps, and let's just quickly go over them. How do I go about doing homogeneous equation? Step A. What do I mean by homogeneous solution? Homogeneous solution is a solution if you assume input is 0. It's a solution if input is assumed to be 0. So you're going to find what the difference equation is doing with no input. And then particular solution, you do the input but without any initial conditions. Then you add them together, and then in order to make the whole thing work, you apply the initial condition. Okay, so here we go. A homogeneous solution. So what is the system if there is no input to it? Remember, this was our claimed system that we were dealing with. This is the primary thing we were dealing with, right? Could you roll up just a tiny bit? Great, thank you. So this is our system. If I let input become 0, I get y of n, a times y of n minus 1. And what's the solution to that? So let x of n equal 0. What's the solution to that? Yeah, it's some constant times alpha to the n. So guess. Just like difference equations, guess the solution is y of n equals some constant k alpha to the n. Plug it in, and what do you get? You get k times alpha to the n is equal to a times, what's y of n minus 1? It would be k alpha n minus 1. And after you solve this, you find that the solution, y sub h of n, is just k times a to the n, some constant. And I don't know what that constant can be anything. That's the loose factor or the wiggle factor for applying initial conditions later, as you'll see. So our homogeneous solution looks like this. If the input is 0, that's the mode of a system. Independent of the input, this system has this mode of a to the n as its solution. Okay? So that's our homogeneous solution. And now we want to find the particular solution. Particular solution, you do the whole thing. Y of n is equal to a times y of n minus 1 plus b times delta of n. And you try to find out what the answer is. And you take the z transform of both sides. Since we just covered z transforms, we know how to do that. So y of z is a z inverse y of z, which is the z transform of this, plus b. That means y of z is equal to b over 1 minus a z inverse. Okay? So how do I find the particular solution? I have to take the inverse z transform of this. How do I take the inverse z transform of this? Depends on the region of convergence. We don't know that. So I'm really going to be thorough about it and consider 2 cases. Case 1, z is larger than that, and I call that case b.1 because this would impart b. In case 2, z is smaller than a, and I'm going to call that b.2. Okay? So I won't dwell on this thing too much. So in case b.1, for case b.1, what do we get as our answer? Particular solution, I call it yp1, is what? In time domain, as a function of n, is what? If the region of convergence is outside of something, this is going to be a right-handed sequence, and I get, what's the inverse z transform of this? It's b times a to the n u of n. And in case 2, which is this guy, yp2 of n is equal to minus b a to the n u of minus n minus 1. We've already seen this like a million times by now this semester, right? And now, step C, I have to combine these 2 answers with each other. So combine particular solution with homogeneous solution. And what do I get? You get y total is y sub h of n plus y sub p of n, particular solution. And again, I'm going to have, and then step D, and y sub p is one of these two things. We don't, there's case 1 and case 2, and step D, I'm going to apply or impose initial condition. And because I have two cases, I'm going to have to impose initial condition twice. But the redeeming factor here is that I get the same answer both ways. I'll show you why. It doesn't matter which way you go. When you impose the initial condition, the answer comes out the same. So let's do that. So impose initial condition. I have case D.1 and D.2. So in D.1, I'm going to assume this guy, y total of n, is k to the a n, which was our homogeneous solution. Remember, this is our homogeneous solution. Plus this as our particular solution, b times a to the n u of n. Apply initial condition, and what you get is it's at n equals -1, so you get y total at n at -1 is equal to we already know the answer is y naught because that was our initial condition from given to us. It's k times a minus 1 plus b times a inverse u of -1. So that's it. And that is going to help us solve for k. And k, therefore, is a times y naught. And in this case, y total of n is, go to the next page. And in this case, y total is just this thing with k replaced by the constant we just found. So y total of n is just a to the power n plus 1 times y naught plus b a to the n u of n. That's encouraging. That's the same thing as we found with method 1. So at least in case 1, we got the same answer as what we had before. Okay? Now, how about case 2? So this is D.1. I put a little box around it. How about D.2? What do I get there? Well, it's y total of n is the same homogeneous equation, k a to the n, plus now I have to plug in my other particular solution, which is y2, right? So it'll be minus b a to the n u of minus n minus 1. And I apply initial condition, which is y of minus 1, y total of minus 1 is equal to y naught is equal to k times a to the minus 1 minus b a to the minus 1 times u of 0. That means in this case, the constant came up to be something else, a y naught plus b. But then by the time I plug in the constant into the y total of n, I get the same answer as before. So if it's a to the n times k, a y naught plus b, minus b a to the n, u of minus n minus 1. And after you do a bit of manipulation, using the fact that u of n plus u of minus n minus 1 makes a constant, which is just 1, you get y total of n is equal to a n plus 1 y naught plus b a to the n u of n. So even in case 2, hallelujah, we got the same answer as case 1. The constants were different, but because they got applied to two different things, at the end they all came out the same. And they corresponded to the same answer we got using the induction method. So this is it. This is the answer. It took a long time to do it, but now we know that that's the answer. So having done it 4 different ways and 9 different ways, does this difference equation now, it now corresponds to a system, a unique input resulting in unique output. Good, good. Now, does it define an LTI system? Even easier, does it define a linear system? So coming back to this system, so conclusion, we get same answer everywhere, all different ways. But the real question I'm asking is coming back to this guy here. Does this define a linear system? And by this, I mean this guy here, which is y of n is a times y of n minus 1 plus x of n, with x of n being b times delta of n, with initial condition being y of minus 1 is equal to y naught. Does it define a linear system? What's a property of a linear system? You add the two inputs, the same output, the outputs get added. You scale the input, the output gets scaled. So the scaling part, yeah. Is this a linear system? Pause. Why not? And y equals what? Right. The answer is no, because for a system to be linear, if you scale the input, the output has to be scaled. In particular, if let a, the scaling factor, not this a, but let the scaling factor be 0. That means if the input is 0, the output has to be 0. This scaling property has to hold true for everything, in particular for 0. That means 0 input has to result in 0 output. And look at this thing. How do I make the input 0? If I make, this is the answer to my problem, to my solution. If I make the input equal 0, that means let b equal 0, the output is still that, which is non-zero. Furthermore, I mean, that's even easier. The initial condition is non-zero. No matter what I do, I always have non-zero output no matter what. Okay, so the answer is no. Not a linear system, because 0 input, i.e. b equals 0, does not result in 0 output. In particular, if we believe in all the answers we got up here, if I let 0 input, let b equal to 0, y total of n is just a to the n plus 1, y naught. It's this thing. It's the y naught that's killing us. How could I make it correspond to a linear system? Yeah. However, if I let y naught equal 0, then it does correspond to a linear system. So strictly speaking, if you have a difference equation, you have to have an IC to make it correspond to a system. That IC, that initial condition, has got to be 0 for it to be a linear system. So that means for LCCDE to correspond, strictly speaking, to a linear system, IC has got to be equal to 0. Initial condition has got to be equal to 0. More importantly, is this, it's coming back to the same system that we have. Okay, so now we're gradually rising up. Now we made it a system. Now we found out how to make it a linear system. Is this a time invariant system? Let's come back here and ask ourselves. So the solution, let me write down the solution here just as a reminder. It's this thing, the solution, right? Is this a time invariant? Well, let's examine it instead of guessing. A system is time invariant is that if you shift the input, the same answer that we had gets shifted. You shift the input, you get a new output. That new output has to be equal to the old output, but just a shifted way, right? So the next question I have is, does this system correspond to a time invariant, TI, not Texas Instrument, but time invariant system? The answer is, let's just try it. So we know that if you let, this is bad also, we know that if you let if the input is b times delta of n, then the output, we just computed it 5 different ways. Y of n is a n plus 1 y naught plus b a of n u of n. That's the output, right? So now let's shift the input. If you shift the input, what happens? Let me just say that now there's a new input. I call it w of n, which is just b times delta of n minus n naught. Now I'm kicking it at time n naught rather than at time 0 with a delta function. Let's just compute the output due to w of n. We can do it 5 different ways again, and I won't go over all the 4 different ways that you could do that, but I put dot, 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 really compute it. And what do I get? I get a n to the 1 y naught plus b a n minus n naught u of n minus n naught. This is after a lot of work, but you can sort of repeat all the steps we did, and you see that this is the output. So this is the output due to w, which is just a shifted version of the input. Now the question is this output the same old output we had but shifted? Is this the same as, let's call it y tot, but at n minus n naught? Well, what is y tot at n minus n naught? Well, it's this thing. Now replace all the n's with minus n naughts and see if that answer you get matches the answer you should have gotten. That's given by a n minus n naught plus 1 y naught plus b a n minus n naught u of n minus n naught. So the question is this thing the same as this thing? Almost. This is the same as that, but this is not the same as the other one. So the answer is no. In general, it's not time invariant. We just went over it. We shifted the input, computed the output, and that computed output is not the same as the old output, but just shifted. So not time invariant. For general, why not? But we can still make it time invariant if y naught is equal to 0. So let y naught equal 0, then it does become time invariant. So my proposition here is that if you wanted this linear constant coefficient difference equation to correspond to an LTI system, you have to have 0 initial condition. Okay, so here's the proposition. For an LCCDE to correspond to an LTI system, must have y naught equals 0, i.e. 0 initial conditions. In particular, if I want it to be causal, furthermore, if I also want causality, then I have to have what's called initial rest condition, and I'll explain what this is in just a second. So then if I have LCCDE plus, I call this IRC, initial rest condition. If I have linear constant coefficient difference equation plus initial rest condition, I get LTI and causality. Now I owe it to you to explain what do I mean by initial rest condition. What's the definition of it? So let's define IRC. So go to a new page. I define IRC as follows. We call the system to have initial rest condition if the output doesn't become non-zero up until the time the input has become non-zero. Okay? So the system has IRC, and I'll define it mathematically now. If and only if, for x of n being 0,
if x of n is 0 for n smaller than n naught, results in y of n also being equal to 0 for n smaller than n naught. That's what I mean. Until the input has kicked in, the output is just 0. So pictorially, what I mean by this is the following. Here's x of n as a function of n. So x of n is 0, 0, 0, 0, 0, 0. And then suddenly at some time n naught, it kicks in. It becomes, a step or something, whatever. It becomes non-zero. Then you say you have initial rest condition if the output also, y of n, is also not 0 all the way here, 0, 0, 0, up until time n naught. Okay? That's pictorially, that's really what that means. Okay? So as an example, if I have x of n being just a delta function, it's just 1. Okay? And if I have a first order difference equation, first order means that y of n is a function of things that are only n minus 1. A second order means y of n has things like n minus 1 and n minus 2 is a function of y of n minus 1 and x of n minus 1 and y of n minus 2, x of n minus 2. That's what the order of a difference equation means. So in this case, if the input is this and I have a first order difference equation, if my input is this, what does it mean about IRC? What's the initial rest condition? It has to be 0 up until the time that this thing kicks in. And that means that I have to have output at time minus 1 be equal to 0. Right? So y of minus 1, this is y of n, has got to be equal to 0 at time minus 1. And now if I changed example 2, if I have x of n equals delta of n minus 5, that means at time 5 input kicks in, then the output is going to be what? The initial condition, initial rest condition, implies that y at time 4 is equal to 0. Okay? Y of 4 is equal to 0. You want to match the initial condition to the input that you're kicking it with. That's the only way mathematically to make that difference equation correspond to a causal LTI system. So if I make the input start at time 1000, then you want y output at time 999 to be equal to 0, just before the thing kicks in. And if it is first order, if it is second order, you want it at time 999 and 998. If it is third order, 999, 998, and 997, etc., etc. So the picture I want you to sort of walk away with is as follows, is that if you have, so that's the meaning of sort of initial rest condition. So the picture I want you to walk away with is that if you have LCCDE and you have initial rest condition, then that corresponds to having a causal LTI system. And that also corresponds to, let's say, with impulse response of Hn, and that also corresponds to a h of z system function that has region of convergence outside of some circle. So these three things are all equivalent to each other. I can go from here to here, there to there, and vice versa. Okay? And I like to also spend the next few minutes talk about the flip side of initial rest condition, which is called final rest condition for anti-causal systems. Okay? So let's talk for a second about what's called final rest condition. It's just the opposite. We call it FRC. Okay? And what that goes is that if we have an LCCDE together plus some initial plus plus final rest condition, that corresponds to an LTI system that's anti-causal. And what do I mean by final rest condition? You say system has FRC if and only if x of n is equal to 0, if and only if for x of n equals 0 for n larger than some n naught, results in, it's just the opposite, y of n also equals 0 for n larger than n naught. That means if x of n as a function of n was non-zero before for all of these values, then y of n also has to be non-zero for all of these values. They get kicked in at the same time. It's just everything flipped the other way. So as an example, if I kick it with delta at 5, then the final rest condition would be that y at time 6 to be equal to 0. Everything just gets reversed, right? So just to wrap up this lecture, let me just go back to this example that we had, which is y of n is equal to a times y of n minus 1 plus b times delta of n. Okay? And suppose that, so if I have initial rest condition for this example, to make this thing to have initial rest condition correspond to a causal LTI system, what kind of, this is my input, x of n, what kind of initial condition should I have? The input kicks in at time 1, at time 0, okay? And so to have initial rest condition, initial rest means it's going to be corresponding to a causality, and therefore, what initial condition would I have to impose to make this an LTI causal system? Y of minus 1 is equal to 0. That same difference equation, if I wanted to have final rest condition, what initial condition do I have to impose? Y of 1 is equal to 0. And then so this corresponds to a causal system, and this corresponds to an anti-causal system. Okay? And so what that really means is that the same difference equation has two realizations or two implementations. So this DE corresponds to two different systems. The same way as if I gave you h of z, without knowing the region of convergence, you don't know if it corresponds to a causal or anti-causal. The same way, this difference equation, you don't know whether it corresponds to a causal implementation or anti-causal implementation. In particular, what I can do is I can have, for this system, I can have what's called a causal implementation. That means y of n takes on the value a of y n minus 1 plus x of n. Or I could have anti-causal implementation, which would mean that y of n minus 1 takes on the value 1 over a y of n minus b over a, or 1 over a x of n. So this is an anti-causal implementation. You compute, if this is y of n, I compute this guy at minus 5 from minus 4. And I compute minus 4 from minus 3. It goes, I'm going this way. Okay, and here I'm going in the positive time direction. So a difference equation just by itself doesn't tell you whether the system is causal or not. A difference equation could correspond to a causal or anti-causal system. Now, if you had even a, again, the picture that I want to write here, saying it corresponds to two different systems, the picture I want you to walk away is LCCDE plus initial rest condition corresponds to LTI causal, I'm repeating myself, and also h of z outside of some circle. Or you can have LCCDE plus final rest condition corresponding to LTI anti-causal, and H of Z with ROC that's inside of some circle. And of course, this is all true for first-order difference equations. If I had a difference equation that was even more complicated, for example, if I had a difference equation that looked like this, how many different implementation can I have? A times yn minus 1 plus alpha times yn minus 2 plus x of n. How many implementations can I have for this guy? How many regions of convergence would this have if I take the Z transform? 3, right? Inside of some circle, between 2, and outside of some circle. And you can prove it by writing H of Z and doing all the manipulations. How many different implementations can I have? 3. I can take y of n taking as a function of y of n minus 1 and y of n minus 2. I can have y of n minus 1 to be a function of y of n and y of n plus 1. Or I can, I can have y of n to be a function of y of n minus 1 and y of n plus 1. Or I can have y of n be a function of y of n plus 1 and y of n plus 2. The same way as I had before here. When I write down y of n minus 1 is equal to that, this is the same thing as saying y of n is the function of 1 over a y of n plus 1 minus 1 over a x of n plus 1. So here I'm writing y of n as a function of n plus 1. In this thing, I can write y of n as a function of 3 different ways. And then I'd like you to go over this concept in the recitation. Okay? I'll talk about this one example a little bit more when I come back next Wednesday. And then we'll dive into flow graphs and implementing IR filters and all that.